here we go. We're going to look at these problems and we'll go from there. If I can get my pen to work. Is my mouse working? Yes. Give me a moment. There we go. Hoshi walks 10 meters in 3 seconds. What is her walking rate? A rate is found by just dividing the two numbers, 10 divided by 3. And that gives us 3.3 repeating meters per second. At this rate, how long does it take her to walk 100 meters? Well, a couple things. You could do some reasoning, but if you don't want to do any reasoning, 10 meters over 3 seconds, 100 meters over x seconds, cross multiply, that gives you 10x equals 300. Divide both sides by 10, and we get 30 seconds. Last one says, suppose she walks at the same rate for 50 seconds. So again, we could go 10 over 3 equals x over 50, cross multiply, that's 500 equals 3x, divide both sides by 3, and so x equals, I think it's 166.6 repeating, but I'll double check here. 500 divided by 3 is indeed 166.6 repeating. And that's meters. So then we want an equation for, this is write an equation that represents the distance that Hoshi walks in t seconds. So we go d equals 3.3 repeating times t. Question number 2. Milo walks 40 meters in 15 seconds. So that's 40 divided by 15. 40 divided by 15 is 2.6 repeating. Myra walks 30 meters in 10 seconds. So 30 divided by 10 is 3. And we want to know whose walking rate is faster. Well, 3 is bigger than 2.6, so Myra. Number 3 here, we have Jose, Mario, Melanie, Mike, and Alicia are on a week-long cycling trip. Cycling times include only biking time, not time to eat, rest, and so on. The table below gives the distance Jose, Mario, and Melanie travel for the first 3 hours. Assume that each person cycles at a constant rate. So we look at the table, and we can see some numbers. So let's see what we want to know. We want to know several things. Find the average rate at which each person travels during the first 3 hours. Well, we can find that by finding the we know that it's a constant rate, and so we can find that by finding the difference of the outputs. So anytime you take 15 minus 10, or 10 minus 5, or 5 minus 0, you get 5. So Jose's rate is 5 miles per hour. Mario's rate is 7 miles per hour. And Melanie's rate is 9 miles per hour. Find the distance each person travels in 7 hours. Well, we'd go 5 times 7, which gives us 35 miles. 7 times 7, which gives us 49 miles. And Melanie's distance would be 9 times 7, which is 63 miles. Letter C says graph the time and distance data for all 3 riders on the same coordinate axis. So we'll do that. We'll start with Jose. Jose, we have a 0, 0, and then we're going to go up by, we'll go 1, 2, 3, 4, 5, 6, 7. I'm going to go out 7 because I know that I was asked for distance for 7, so I might as well go out 7. I also know that in the next question, it says that we're going to find the distance for 6.5 hours. So then I'm going to go up by 10s here, 10, 20, 30, 40, 50, 60, 70. Because I'm going to be asked a question about use graphs to find the time it takes each person to travel 70 miles. So want to just stop and see some of those things. All right. So 1 and 5, 2 and 10, 3 and, there we go, just going up 5 each time for Jose. And you know what, 8, 9, 10, might as well do this because I know what's going to happen later on with this part of the problem. So there we go with Jose's graph, and then let's do Mario's graph. He's 1 and then 7, and then 14, and then 21, 28, 35, 42, 49, 56, 63, and then 70. And then let's go with purple for Melanie. So she starts off at 0, 0, but she's at 9, and then she's at 18, and then she's 27, and then 36, and then 45, and then 54, and then 63, and then 72, and then 81, and then 90. So here we have our graphs. I could put lines through them, but I'm not going to because that will take too much time. It says use the graphs to find the distance each person travels at 6.5 hours. So 6.5. If we look at our graph, 6.5 is right through here. And so if we were to look, I'm going to connect these points here, and I'm going to connect these points here, and I'm going to connect these points here so I can see this better. There's the 6.5 line, and if I look, Jose's distance is going to be somewhere between 30 and 35, so I'm going to say it's 32.5. Mario's distance is somewhere between 42 and 49, so 42, 49, 7, so 45.5. And then right here we've got 54 to 63. So 54, if I 63, 54 minus 63 is 9. There's a 9 gap, so 4.5. So that's, and it's between, I mean, yeah. Long story short, it's like looking somewhere between 55 and 60. So I guess I could be more specific. It is 58.5. But we're just reading that from, like, we're reading this point here, and this point here. So if you looked at them and just said, hey, 33, and then right here you're just going to say 45, and right here you're just going to say 57, I wouldn't mark you wrong because you're reading from the graph and those parts aren't scaled that way. So the next question says, use the graphs to find the time it takes each person to travel 70 miles. Well, 70 miles is across here. And so we can find Melanie and Mario's time really easy. Melanie is at about 8 hours, whereas Mario is exactly 10 hours. And Jose's time, Jose doesn't even reach 70 on this graph. Now, if you stop and do some reasoning, you know that it takes Jose 7 hours to get to 35, so double that would give you 14. Or you could go 70 divided by 5 equals 14. But that does defeat the heart of what we really want you to see here, and that's the fact that graphs can sometimes be difficult to use. So letter F asks us, how does the rate of each person's rides affect each graph? Well, the faster the rate, the steeper the graph. Then we want equations, so y equals 5x, y equals 7x, and y equals 9x. Because remember that the rate of change is the coefficient. Use your equations. So now this is so much easier. 5 times 6.5, we throw that in the calculator and we get 32.5. Y equals 7 times 6.5. Again, So much easier. Y equals, you throw that in the calculator, you get 45.5. Y equals 9 times 6.5, and again, so much simpler. It's just 58.5. This is the benefit of the equation, is that you can use that equation so much faster. So how does each person's biking rate show up in the equation? The rate is the coefficient. All right. So we look at, for Mike, Mike makes the following table of the distances he traveled during the first day of the trip. So we look here, Mike's rate is a constant rate and it keeps going up. It says, suppose Mike continues riding at this rate, write an equation for the distance Mike travels after t hours. So distance equals 6.5 t, because his rate just keeps going up 6.5 each time. Sketch a graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I can see that I'm going, so my domain just right now is 0 to 6. My range, 0 to 39. So I don't see a good reason to not just go by tens. So 10, 20, 30, 40, 50. I only need to go up to 39, but I'm just going to go by 10 still. So 0, 0. So the first point for Mike's graph is 0, 0. Next point's 1 and 6.5, 2 and 13, 3 and 19.5, 4 and 26, 5 and 32.5, 6 and 39, and there we go. We've got Mike's points plotted. And the reason why we chose the range of values for the time axis was because the domain I was given was 0 to 6, and for the distance axis, the range I was given was 0 to 39. Now these questions here are simple written sentences. How can you find the distances Mike travels 7 hours and 9.5 hours using the table? Well, if I were to use this table here to go 7 hours, I would continue adding the constant rate. As far as the graph goes, you would need to say something along the lines of, I would extend the graph. Plot a couple more points. As far as using the equation, you would substitute for x and solve. Now the next one says, how can you find the numbers of hours it takes Mike to travel 100 miles and 237 miles using the table? This would be, I would extend the table until y, or distance, is 100 or 237. For the graph, I would continue plotting points. And for the equation, we would actually just substitute for y and solve. So the next question then says, for parts C, D, and E, well, C, and D, what are the advantages and disadvantages of using each form of representation? Well, the table is good for known or close values. It's also good for multiples of the rate. So if you have multiples of the rate, then it's good. The graph, it's good for known values again, and for close values. It also makes a good estimation tool. But the equation is just simple algebra. And right there, that's what makes the equation superior to the table and the graph. Because once you get big numbers, the table and the graph, or numbers that are very far from what data you've plotted or have at the start, the graph and the table become useless. So fastest. Compare rate at which Mike rides with the rates of Jose, Mario, and Melanie ride. Who rides the fastest? Well, Melanie's at 9, so that's Melanie who's the fastest. Melanie. And this should be part of F. How can you determine this from the tables? Rate of change from the table. From the graph, it's the steepest slope, or steepest line, I should say. And from the equation, it's the coefficient. So number 5. The distance Alicia travels in T hours is represented by the equation 7.5. What rate does she travel? 7.5 miles per hour. Suppose that the graph of Alicia's distance and time is put on the same set of axes as Mike's, Jose's, Mario's, and Melanie's graphs. Where would it be located in relationship to each of the graphs? Well, it would be below Melanie, above the others. All right, now we're into some pledge plans. Describe sponsor A's pledge. Sponsor A donates, and I'm going to look at this. It goes from 0 up to 3, and then up to 6, and then up to 9. So sponsor A donates $3 per kilometer. Sponsor B donates just $5, that's all. Sponsor C, flat $2 donation plus, this goes up 1, 2, 3 over 2. So it's increasing $1.50 per kilometer. So what's the number of dollars per kilometer each sponsor pledges? So we have $3 per kilometer here, we have $0 per kilometer here, and we have $1.50 per kilometer here. So letter C, what does the point where the line crosses the y-axis mean for each sponsor? The flat donation, or donation without kilometers. Write the coordinates of 2 points on each line. So the first one, we'll do 1 and 3. What information? It means 1 kilometer gets you $3. Sponsor B, if I go 1, 5, that means 1 kilometer gets you $5. And then sponsor C will go 2, 5, and that means that 2 kilometers will get you $5. For each company, so the students in Ms. Chang's class decide to order water bottles that advertise the walkathon. Malik obtains 2 different quotes for the cost of the bottles. Fill It Up charges $4 per bottle. Bottles by Bob charges $25 plus $3 per bottle. For each company, write an equation Malik could use to calculate the cost of the number of bottles. For Fill It Up, that'd be y equals 4x. For bottles by Bob, that'd be y equals 3x plus 25. So part B says, on the same set of axes, graph both equations from part A. Which variable is independent and which variable is dependent? Well, the independent variable is bottles, and the dependent variable is money. Now, if I look here, because I can interpret the problem here, 4x, that's going to start off at 0. And the other one is going to start off at 25. And so I'm going to go by 5s because, so 5, then this would be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so going to start off, we're going to go up 4 over 1. Wait a minute. If I keep going up 4 over 1, that's going to be a very slow rise. Let's not go by ones. Let's pick a different number for the bottles. Let's go, and actually, because I'm thinking about this, to get up to 100 bottles, I need 25 bottles for this one. So why don't we make this let's see. Well, let's have this do 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now, the beauty of this is that we know all we have to do is multiply 4 by 10. So 4 times 10 is 40. 80 times 30 is off the graph, but I can go back and do 4 times 5 is 20, times 10 is 16, and then 20 right there. So there we have our graph of 4x. And our graph of 3x plus 25, we can start off here. And let's just go ahead and multiply. 3 times 5 is 15 plus 25. So we're doing 15 plus 25 gives us 40. So, and then 10 times 3 is 30 plus 25 gives us 70, no wait, 30, it gives us 55. And then 15 times 3 plus 25 gives us 70. So I'm making a table without making a table for those of you who are like, what's he doing? I'm just not drawing out a table for this. I'm just actually like putting in the numbers and getting out valid answers back. So 3 times 20 plus 25 would give us 85. And then we'd actually meet up right there, which is an important piece to this problem. So, letter C, which company do you think the class should buy waters from? What factors influence your decision? So, if you're buying less than 25 bottles, then you want to choose Fill It Up. If you're buying more than 25 bottles, you want to choose Bob. Because it's cheaper then. So the things that we were concerned about are bottles and cost. We're not concerned about anything else other than bottles and cost. So letter D. For what number of water bottles is it the same for both companies? 25 bottles. Number 8. The equation C equals 5N represents the cost in dollars for end caps that advertise the walkathon. Which of the following pairs of numbers could represent the number of caps for the cost? So we just put the numbers in. 0 times 5 is 0, so it's not A. 3 times 5 is 15, so that is B. B would work. 5 times 15 is 75, so C doesn't work. And 5 times 5 is 25, so D doesn't work. Number 9. The equation D equals 3.5 T plus 50 represents the distance in meters that a cyclist is from his home after T seconds. Which of the following pairs of numbers represent the coordinates of a point on the graph of this equation? So we take 10 10 times 3.5 plus 50, that equals 85. So I, or Roman numeral 1, and here's why it works, is because 3.5 times 10 plus 50 equals 85. Number 2 isn't going to work because if we put 0 into this, we'll get out 50. Let's see if number 3 works. It's going to be 3 times 3 plus 50. Well, 3 times 3 point, sorry, that should be 3.5, sorry. The 3.5 is the rate. So, crikey. That's 3.5 times 3 plus 50. That gives me 60.5. So the point 3, comma 60.5 is also a point that's going to work. What information do coordinates represent about the cyclists? It represents the distance d after time t. So similarities, you could come up with all sorts of things, as well as differences. You could come up with all sorts of things. So you could talk about the rates of change in these things are different. Some of them are constant, some of them are not. You could talk about the similarities in the fact that like x values are increasing. So explain how you can use the tables to decide if the you can find a constant rate of change. Find a constant rate of change. To graph these, -2, 3 would be right here. -1, 3, 0, 3, 1, 3, 2, 3. Second graph, -3, 9 is all the way up here. -2, 4 is right here. -1, 1 is right there. 0, 0, and 1, 1. The third graph, this one's funky. 0, 10. So we're going to have to change our grid here. If I go by 10s, that should be good enough. Actually, you know what? I'll go by 5s. So 5, 10. So 0, 10. And then 3. Oh, I need to change these around too then, because that's 12 off the grid. So we're going to go by 2s.
Sorry, teachers, for the interruption. Carter Thayer to the office, please. Carter Thayer to the office.
19. And then 5, 25. And then, so it's 2, 4, 6, 8, 10. Goes up to 40. So that's 5, 10, 50. So 1, 2, 3, 4, 5. That's 10 right there. And then 5, 10, 15, 20, 25, 30, 35, 40. That's up there. So that's going to be right there. And then we have 12 and 46. So that's right there. And that's up around there. Whew, that's a weird graph. This one's a little scary. We'll have to talk about that. And then number 4. Number 4 is 0, -3. Well, I'm going to go by 3. 0, -3, 2, -6, 4, -9, 6, -12, and 8, -15. Oh, oops, 8, -15 is right there, not that point there. So explain how you can use the tables to decide, so we can look at the constant rate of change. Sketch the graph in each table. Okay, we did that. Write an equation for each linear relationship. Well, if we look at this, the first one, that's just y equals 3. That's definitely linear. The second one is not linear. The third one, that looks like a line. So we're going to have to do some inspection here. It looks like a line, but our constant rate of change is awfully hard to find. So let's take a look at this. We have 0 to 3 is 3 change and 9. 3 to 5 is 2, and 19 to 25 is 6. Oh, well, that's interesting. 5 to 10 is 5, and then 25 to 40 is 15, and then 10 to 12 is 2, and that's 6 again. Now, if I look at this, it doesn't look like it's a constant rate of change yet, but think this through here for a moment. Every 3 steps, I went up 9. Every 2, I went up 6. Every 5, I went up 15. Every 2, I went up 6. So that means that our rate of change is actually 3 per whatever. So this actually would be y equals 3x plus 10, because we're starting at 10. And then table 4 is y equals, we're going down 3 each time, and we started down 3. So that's actually, number 3 is very exciting. That's not a test question. That's a crazy thought. All right, number 11, finishing this up. Temperature at the North Pole is 30 degrees, expected to drop 5 degrees. So here we go. I need to finish this quickly. Drop 5 degrees in 30. So what do the parts mean? Y is temp. -5 is rate. X is hours. And 30 is start temp. Yes, it's linear. Number 12, Jamal has $20 at the start of camp. He spends $2 each day. Yes, it's linear because it's a constant rate. Because class is about to start, I'm going to have to finish this video up a little later on because I don't see a pause feature.